Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today we're going to be talking about how to use mesh analysis for an RLC circuit. I'll be doing an example. So here's a circuit given. It's similar to circuit shapes that we have looked at in the past, but in the past we've only looked at circuits with independent voltage sources and current sources and resistors. So now we're going to add in the the capacitors and the inductors. So here's a circuit with some values given. What we are asked to find is the relationship of the output V out of t in terms of V in of t. Now we're going to do this in the LaPlace domain. So what we're actually looking for is the transfer function V out of S over V in of S. So here's my circuit redrawn. And this time let's go ahead and we'll use mesh analysis. And knowing how to do this is best illustrated through an example. So we'll start with the circuit. I'm going to define I1 going around this way and I2 going around this way. Now we can write these again in the LaPlace domain with the S's shown. That would give us, this would be V of S, and this would be V in of S. This would be plus or minus V out of S. Minus V1 of S plus I1 times R1 plus I1 minus I2 times the impedance of that inductor. We can write this using the LaPlace versions of the impedance. We just have minus Vn of S plus I1 of S times R plus I1 of S minus I2 of S times S times L equals 0. Okay, plugging in our values, we get minus Vn of S plus I1 of S times 4 ohms plus I1 of S minus I2 of S times S times 2 henries equals 0. Now let's go around the other loop. Okay, so this was mesh 1, here will be mesh 2. We have I2 of S minus I1 of S times ZL times S, SCL. Well, I guess I don't need the S if I write ZL. So ZL plus I2 times ZC plus I2 times R2 or ZR2 equals 0. So plugging in for our values, we have I2 of S, plug in for the impedances. I2 of S minus I1 of S times S times L plus I2 times ZC. Oops, and ZC is 1 over SC plus I2 times ZR, which is just plain old R. Now when we plug in values, we get I2 minus I1 times S times 2 plus I2 times 1 over S times 1/4 plus I2 times R. And R is, I should have plugged in value for R, and R was 4. Okay, now we have to solve algebraically. You can't do this numerically. You have to do algebraic solving, and I usually use successive substitution. So we only have 2 equations. This is actually going to be tractable, so we can do that. Let me just copy these equations over. Oops, well there they are written. And I have this written out, so let me just show you that worked out. So first thing we do is we don't need to write the dependence on S, so we don't need to do that. So we will drop all the I2 of S's and just write I2. We use a capital letter so that it's clear that we are talking about the S domain. And then if we just multiply that second equation by S, that will clear the S from the denominator, and we end up with this equation here. Then if you collect the like term for both equations, we end up with these two equations. Okay, so this is only algebra. It's a bit messy. There's some things you can do to make it a little bit easier for yourself, like not writing the I1 of S and just writing I1. I also think that most students do better if you plug in the values as soon as you have them rather than keeping them as I did before with R's and L's and C's. Okay, so over here, I wrote it all out. It's messy because I've got these, you know, the S dependence is shown, but it's also messy because I went ahead and wrote these intermediate steps. Okay, as of this moment, I don't expect you to write those intermediate steps. You can just go straight to this equation and straight to this equation. Okay, now just to reiterate, we'll take this equation, multiply it through by S, so we'll end up with an S squared here. That'll clear this denominator, and then we'll end up with an S term there. And that's where we get this equation. Okay, so here's the two equations where we put the one equation on the, where we basically have both functions of S equal to some constant. Okay, so what we're going to do is take that second equation, solve for I1 in terms of I2. Okay, simplify it, and then substitute it back into the first equation. And this is very messy. This is unavoidable. Okay, so what I usually like to do is when I have an S in the denominator, anytime I have a denominator, just multiply through the whole equation on both sides by that value, and you will end up with something that's a little bit nicer to look at. So we take this equation, multiply the whole equation by S squared. That will give us 2S plus 4 times S squared plus 2S plus 2, so that S squared in the denominator went away, times I2. And then here, that's where we get an S to the cube, S to the third. And of course, we have to multiply both sides, so we have an S squared over here. So now we just collect like terms. Well, I guess the first thing we do is multiply this whole thing out. Okay, then collect like terms, and then solve for I2 in terms of Vn. Now, this is a good moment to think, where were we headed? What did we want to find? We wanted to find H of S was equal to V out of S over Vn of S. So here we have a relationship that shows I1 and I2, but what we really care about is V out and Vn. Now, at this point, don't worry that you've got a Vn. You've got two equations, right? Here's an equation for I1, here's an equation for I2. We have three unknowns, I1, I2, and Vn, but Vn is going to be part of the quantity we're looking for, so that's not going to be a problem. We can write an equation for V out. V out is just going to be, remember, V is equal to IR. Okay, we just had an equation for I2 of S. We multiply it by 4, and we end up with this. Divide by Vn because we care about the ratio, and that gives us our transfer function. This is all we need. Notice that we did not need to find I1 of S. So always pay attention to what you need to find so you don't have to do extra work.